Hey everybody, I hope you're doing well as you begin this lesson here on curve sketching. Curve sketching is going to take concepts that we have seen with the function and their derivatives and understanding how they behave with each other, meaning that if a function is increasing, its derivative is going to be positive. If a function is decreasing, its derivative will be negative along whatever increasing or decreasing intervals that they have. And it's also going to utilize the first and second derivatives that we've seen previously to identify where I'm going to have maybe a maximum value, minimum value, where I'm concave up, where I'm concave down, things of that nature. So what we're going to be asked to do when we do our curve sketching is we want to be able to identify what is the domain and range, where do I have any intercepts, asymptotes, anything like that? Do I have any critical points that are going to tell me where I might have increasing or decreasing intervals? Identify relative extrema and concavity, and then be able to sketch the function, sketch a curve of the function. Now, some of the stuff that you'll see, you should be able to have a decent idea of how the sketch should look in the beginning, just based off of prior understanding of functions. Here you can go ahead and add this into your notes if you would like. This is just going to be a kind of a rough idea of what we're going to be doing with curve sketching. So if my function is increasing like you see on the, like in quadrant 2, or if it's decreasing like you see in quadrant 1, that means that my derivative is either going to be positive or negative at those points. If my function is, the second derivative is negative at that point, then the function will be kind of concave down, regardless of where it is, regardless of what the first function is doing, whether it's increasing or decreasing. If my second derivative is negative, that's indicating that that function, the primary function, should be concave down along some interval. Then we would look at it as, okay, well, if the function is decreasing, if we're decreasing or increasing in the lower quadrants of our graph here, what is the function going to do? Well, if we're decreasing, again, the derivative itself will be negative, while the derivative will be positive whenever my function itself, the primary function, is increasing. And here, and I forgot the concavity here, this is, again, kind of illustrating that whenever the second derivative is going to be positive, regardless of what my function itself is doing, that's going to show you that you're going to be concave up at that point, which kind of makes sense. We want it to go down one way and then up the other way for it to be concave up. So this is just kind of a rough idea, a rough kind of thing that I put together to help you kind of visualize what the functions are going to be doing. But let's take a look at our first example. We have a third-degree polynomial. Now, the third-degree polynomial, in and of itself, really shouldn't be that much of a surprise. What we're going to see for something like this is we should understand what its end behavior is going to be. Is the leading coefficient is positive, so that means the left side will go down and the right side will go up. Without identifying any particular roots or anything like that, I know I'm going to have a y-intercept somewhere of about -2, according to what that is. So we're going to have something that is going to go something like this. And I don't know if where I'm exactly supposed to be, but we'll have something along these lines as far as what our function should look like. And, we should have a maximum value before I have a minimum value on whatever intervals that we wind up with. But we have to do some kind of analysis to figure out where those things are going to be, and that's what we're being asked to do here. So the first thing it's asking you to do is identify what is the first derivative. Well, the first derivative here is going to be pretty easy to get because it's a polynomial function. The derivative itself, probably you can just do that in your head to get to 3x squared minus 12x plus 9. But we want to solve this. We want to set it equal to 0 and solve it so that way we can identify what its critical numbers are. So I'm factoring out 3 as a common factor, and then I'm going to factor the quadratic that I have remaining in parentheses to be x minus 3 and x minus 1. So that's going to tell me where those are the critical numbers at positive 3 and positive 1. That's going to tell me where on my function itself I'm going to have a minimum or a maximum value. And my guess, based on what the function I know should look like, my guess is that this x equals 1 is going to give me my minimum value, where this x equals 3, that's probably going to give me a maximum value, because again, the function itself is doing one of these things here, so I'm going to hit, I have that backwards. Glad I took a look at the sketch again. So the 1 is the first thing that we're going to hit, so that one should have a maximum value. And the 3 is going to be the second value that we hit. So this one I should have a minimum value at. Minimum, not mim. And, if I want to know what those actual numbers are, I would take them and plug them into that function there to see what their corresponding outputs would be to find the minimum or maximum. And we will, because that's one of the things that you're being asked to identify. So based off of that, I can have a candidates test here where I look to the left of the 1 on the derivative, and it's like, for instance, if I just substitute 0 into the function, if I substitute 0 into the derivative, I'm going to be left with a positive 9. So anything to the left of the 1 is positive. The numbers in between the 1 and the 3 on the first derivative are going to be negative, and numbers to the right of the 3 are going to be positive. And we can almost see the concavity just based off what we're seeing here. We can see it's coming up, going down, and then going up again, which makes, again, a lot of sense compared to considering what we're looking at for a third-degree polynomial. So now I want to do the same thing for my derivative, because now we can identify the increasing and decreasing intervals of the function based on what the critical numbers of the derivative gave us. So second derivative is going to be 6x minus 12, and again I'm going to solve this so that way I can find the critical numbers here. So in this case, x is equal to 2. And that, where the x value is equal to 2 for the second derivative, that will translate to an inflection point on the function itself. So and again, we're going to do our candidates test with the second derivative. If I pick a number to the left of the negative 2, say a 1, I'm going to get a negative output, meaning that the function is going to be concave down. And if I pick a number to the right, say 3, that would result in a positive number on the second derivative, indicating that our function should be concave up, which again kind of makes sense, because what we are seeing here in the first derivative test, we're going to have some kind of pattern like that. And of course, if I'm concave down, and then I'm going to change to being concave up, right there where x is equal to 2, that again kind of matches the behavior of what our third-degree polynomial should be. So what we're going to do now is take all that information and sketch the function and identify all the things it was asking us at the beginning, like what's the domain and range, any intercepts and things of that nature. So here it's a polynomial function. The domain will be all real numbers. Same thing with the range for the odd degree. The y-intercept is given to you in the standard form of the equation at -2. Now to find the minimum and maximum, we take the critical numbers of the derivative, and we plug those into the primary function to find where the min and max are. So I have a minimum at -2 and a maximum at +2. Based on what the first derivative candidates test told me, we should have increasing intervals from -infinity to 1 and 3 to infinity. And my only decreasing interval is going to be between 1 and 3. My inflection point, which is the critical number of the second derivative, in this case worked out to be at 2. So when x is equal to 2, that's where I should change concavity. Now it didn't tell us, and I forgot to type one here. We have two roots given to us. Excuse me, I apologize. But we also have another root at x is equal to a +2 that I've neglected to put there for some reason. And again, based on the second derivative candidates test, we are able to identify the points, or the intervals, I should say, where the function is concave up and concave down. So using all of that information, ideally we can be able to, we can sketch a graph of the function, and it should look something like this, where we have a y-intercept at -2. We have a maximum value at x is equal to 1, which in this case the maximum value is 2. When x is equal to 2, that's where my point of inflection is, which happens to also be a root of the function. My minimum value is going to change, or going to be at +3 and -2, and that's again where it's going to change directions, so that matches with the increasing and decreasing intervals that we got from the candidates test. And this is again what the basic sketch of the function should look like. So it's a little bit different than trying to identify any rational roots using our rational root theorem with p's and q's, and then maybe having to do like maybe some kind of a synthetic division or something to identify where I'm going to have something else that I could factor to identify any roots with. So it's similar to things you would have done in, say, pre-cal or college algebra when you're graphing a polynomial function, but here we're identifying the same things that those classes would have done, but with our curve sketching skills from what we know about when the function is increasing and decreasing based off of its what its derivative should look like, where the mins and maxes are going to be, where it's going to be concave up and concave down based on the first and second derivative tests. So that's the first example. Now let's take a look at this one. Now this one gets quite a bit more complicated. Now again, before you even begin, you can kind of visualize what the function is going to look like. Here, the roots, remember, come from the numerator, and the vertical asymptotes come from the denominator. Now if I try to set the numerator equal to 0, we're going to get non-real answers, so there's no real roots here. And the vertical asymptote, if I set that equal to 0, I'm going to have vertical asymptote at a positive and a -3. So we can have vertical asymptote here, vertical asymptote here. My y-intercept will be the ratio of 1 to 9, so it's going to be something very close to the x-axis, but it's going to be negative. And we have because the function is balanced, I'm going to have a horizontal asymptote at a +1. So nothing is coming together at a vertical asymptote, so I'm imagining this is kind of what we're going to be looking at, something like this. So you can see based off of the rough sketch that I have, and again, you should be able to have some idea what it's going to look like prior to doing anything based on prior knowledge, things that you would have done in, say, Algebra 2, pre-cal, or college algebra. In this case, we can see intervals of increasing from -infinity to +3, and from +3 to 0, and I have decreasing intervals from 0 to +3 and from +3 to infinity. And okay, that's giving me a good idea of what I should have when I do my candidates test for my first or second derivatives. Now what it's asking you to do here, we have to find the first and second derivatives. Now this one we have to use the quotient rule to really identify what the derivative is going to be. So low d high minus high d low over low low gives me this expression. Do all of your distribution and combining any like terms that you have. Okay, and in this case we're going to end up with the derivative of -20x over x squared minus 9 quantity squared. Okay. Now, same thing here, as I'm going to want to take, and I skipped a step here, I want to take the numerator and the denominator, and I want to set those equal to 0 to see where I'm going to have some critical numbers at. And in this case, I'm going to have critical numbers at 0 and positive -3. Now, the positive -3, those are very much going to correspond to where we suspect the vertical asymptotes are going to be. So here, when I, again, take the numbers that are to the left of the -3, to the left and right of 0, and to the right of the +3, when I take those and plug them back into my first derivative, remember, the first derivative test to see where it's increasing, decreasing, we're looking at the expression that we have for our first derivative, and what the candidates test is showing me is basically what I was suspecting it was going to look like, where it's going to have two increasing intervals, because -3 is going to have a vertical asymptote, so I have an increasing interval to the left of it and to the right of it. But then when I get to 0, when x is 0, that's where our y-intercept was. That's where we changed directions. And we started going down, and we had two consecutive downward intervals there that we had for our for the function that we just kind of sketched to see what it was going to look like. Now to do the second derivative is going to get a little wonky here, because we have to, again, we're taking the derivative of the first derivative, so I do have to use the quotient rule again. So this is how it gets set up. X squared minus 9 quantity squared times -20 minus -20x times the high parts derivative, the low parts derivative, which would be 2x times 2 times x squared minus 9. And we're having to use a little bit of the chain rule again on that denominator, unfortunately. But that's what the second derivative is going to be when we set it up. Now go ahead and multiply through everything in the numerator, so that way you can identify any like terms that you're going to need to combine. And here, this is where I'm done. There we go. So essentially what I'm doing is I'm factoring out a 3 of the parenthesis in the numerator, and that's how I'm getting 60 in the numerator times x squared plus 3 over the quantity x squared minus 9 quantity cubed. Now, in this case, the numerator is not going to be able to be set equal to 0, because, as we established at the beginning, there aren't any real roots here. So the numerator can't be set equal to 0. And if you just try to set that expression, x squared plus 3, and you set it equal to 0, that's going to give you imaginary numbers. So no real roots here. So the expression in the denominator, the x squared minus 9, it will have two factors, or two values, that x could be a positive or -3. So again, those are kind of correlating to where the vertical asymptotes are going to be, and that should again let us know where our function is going to be concave up or concave down. So I'm going to do another candidates test, and I have to pick something to the left of the -3, something in between the positive and -3, and something to the right of the positive 3. Now remember, all those numbers that we're picking for the candidates test go into the expression for our second derivative, the 60 times x squared plus 3 over the x squared minus 9 quantity cubed. That's our second derivative. And again, it kind of makes sense based on what we had. Again, just to throw that sketch back up here, we had x and y axis. We established that we had roots at positive -3, y-intercept very close to 0. That we're going to have something like that, and like that. And so you can see here we are increasing, here we are increasing, here we're decreasing, here we're decreasing. So that matches everything that was in the candidates test of the first derivative. And let's pick another color here where they're showing us that they're concave up. So here I'm concave up, and here I'm concave up, which matches what we're seeing in the candidates test for the second derivative. And here in the middle, between the 3's, we're concave down, which again matches what the candidates test is showing us. So again, you should have an idea of what the sketch should look like, because, I mean, it's a rational function, but we've all studied rational functions already. So I was able to do all that without any calculus, but the calculus is just kind of confirming what I suspected it was going to be from the just what I know about rational functions and how to graph them. So the domain is going to include every number except for positive and -3. The range is going to include every number except where we have that horizontal asymptote at y is equal to 1. The y-intercept, in this case, horizontal asymptote, can't read what I'm writing. Horizontal asymptote is at 1. The balanced function, x squared over x squared, simplifies to be 1. Vertical asymptote is positive negative 3. Increasing interval is decreasing interval is y-intercept at negative 1/9. And the two intervals that show where we're concave up and the one interval that shows where we're concave down all kind of match. And here I just took a screenshot from a calculator that I had and put it in here because it was getting funky to try and graph it with anything else. But that's how we're going to be looking at our first and second derivative tests, along with anything else that we would have for, just understanding, the relationship between the function and its derivative. When the function is increasing, what does the derivative do? When the function is decreasing, what does the derivative do? So that is how we're taking some calculus using the first and second derivative tests and identifying where we're going to be at. And let's see. Oh, I just kind of messed something up. I don't want to do that again. The stuff that I have written in that green marker on the board, that's really not supposed to be there right now, but I have a feeling if I take it away, I'm going to take everything away. So anyway, now what we're being asked to do is they're not giving us a nice function that we can work with, right? Because we had the polynomial function and the rational function, and we knew a lot about polynomial and rational functions and how to graph them beforehand. Now here they're not giving us that. They're just telling us what the behavior is on the first and second derivatives, and then we're being asked to, well, based off of what we're seeing here, can we sketch a graph of the function? And this one's going to take a little bit more practice because we don't have that prior knowledge to fall back on and say, okay, well, I know what it should look like based on this other information I have. So here, based on what we're seeing, they're telling us that we have our first derivative is going to be greater than 0 from negative infinity to negative 3. So if my derivative is positive along that interval, that means my function has to be increasing, which is why I have that arrow going up to the left of the negative 3. It also tells me that it's going to be that the derivative is positive between 1 and 4. So that's why on my candidates test there that I have with the little table, between the 1 and 4, I have an arrow also pointing up, showing that it's increasing. Well, we have two intervals where the function's derivative is negative, between 3 and 1 and 4 and infinity, and that's where those down arrows are showing. So this candidates test that I'm looking at here, showing the increasing and decreasing stuff, this is just giving me an idea of what the function shape is going to look like. We know we're going to start with an increasing interval that will be concave down to a decreasing interval, which will be concave up, heading into another increasing interval, and then turning downwards again after we pass the 4. Now, part C says the second derivative is going to give us something that's negative on the interval is negative infinity to negative 1 and between 2 and infinity. And that kind of makes sense with what we're seeing here, even though I haven't done the second derivatives candidates test here. We're clearly going to be increasing somewhere here, giving us, and then decreasing, giving us something concave down along that interval. And between 2 and infinity, so something to the right of the 1, so I think that probably should have been a 1. We're going to be going up, and then we're going to be coming down again. So we can kind of see what the increasing and decreasing intervals are going to be. And let's see, where it does tell, on part E, the first derivative is going to be equal to 0 at that point. So that tells us where the slope is 0. So that means that we're going to have a maximum at 3. And we're going to have a maximum at 4 also for us to have a slope of 0. That'll be our horizontal line. And I have my second derivative is 0 on 1, negative 3. I'm sorry, negative 1, 3, and 2, 4. So that's where we're going to have some type of inflection point. So based off of what we know here, and here's my second derivative candidates test. We should be able to have some sketch that looks kind of like this. Now, if you did this on your own before I did it, then your graph may not be identical to mine, but that's okay. We're not looking for accuracy necessarily here. We're just looking to see, are you able to identify the behaviors, where is it increasing, decreasing, etc., based on what the information told you. Now the next one is going to be pretty similar, but they're throwing in a couple of things at the bottom, particularly G, where it says it's differentiable everywhere except at x is equal to 0. So the only way that the function cannot be differentiable somewhere, because it tells us it's continuous over all real numbers, the only way that it could be continuous but not differentiable is if there's a corner somewhere. So at x is equal to 0, I have to have a corner somewhere. And what I want you guys to do now is go ahead and pause the video, try to come up with a sketch of your own based on the information that's given to you, and then hit play and see what my answers are going to look like, what my graph is going to look like here. All right, so hopefully you've done what I've asked you to do, but let's take a look at what we have. The function is having a derivative that's positive on the interval from negative infinity to negative 2, and from 0 to 3. So we're increasing, my function has to be increasing at those points. My derivative is negative from 2 to 0 and from 3 to infinity, so that means from those intervals they have to be decreasing on the function. My second derivative is going to be less than 0, so meaning it's going to be negative there, so that means I'm going to be concave down from the interval from negative infinity to 0 and concave down from 0 to infinity. And part D tells me that I'm going to have only one interval where I'm concave up at 5 to infinity, because that's where the second derivative is positive. We should have a max or a min, a relative extrema at negative 2 and positive 3, because that's where the first derivatives are equal to 0. And here they're showing you that f prime of 0 doesn't exist, which means that it's not differentiable there. So that f and g are kind of telling you the same thing. It's not going to be differentiable there. And that we have to include an inflection point at 5 and 1. So this is the graph that I came up with. Now your graph doesn't need to match mine, like I said, exactly. They don't need to be verbatim, but the basic shape should be the same, as far as you should have two regions where you're concave down from about, where were we concave down at? From negative infinity up to the 0, and from 0 to the 5 we're concave down. The only place that we're concave up on the function is going to be from 5 to infinity, and that's kind of what we're seeing at the right end of the graph that I have there. At negative 2 and negative 3, because of the concavity, those both have to be maxes. And to show that the function doesn't exist at 0, or that it's not going, or not that the function doesn't exist, but the derivative at 0 doesn't exist, I put a corner there, or a cusp, whatever you want to think of it as. And then at the very end on the far right at 5,1, I had that inflection point where it changes from being decreasing to increasing, or from concave down to concave up. So there we go with that one. Now, the last thing that we're going to be looking at here is just kind of telling you what are some steps that you have to do in order to be able to go from the function, or to sketch the function given the derivative. And that's going to be a big deal because generally when the AP test is going to give you a graph of a function, the graph is actually the derivative of the function. So you need to make sure you read the question. Are they giving you the function, or are they giving you the derivative? And usually they try to give you the derivative and then ask you something about the function based on what you know the derivative and its primary function are supposed to do. So here we want to be able to identify any critical numbers of the derivative, because that's where it shows you you're going to have mins and maxes at. We want to be able to identify where the function is increasing or decreasing based on whether the derivative is above or below the x-axis, meaning it's either positive or negative. We want to identify any kind of increase or concave up or concave down regions based off of what the second derivative tells us, whether we're going to have a negative number to the left or right of our critical values, or a positive number to the left or right of our critical values to tell you whether we're either going to be concave up or concave down. And somewhere, there we go. Finally, you just sketch the curve and see what it looks like. So here's our last task for this particular lesson. And again, they're showing you, can you sketch the graph of the function given the derivative? So this parabola that you're seeing is the derivative. And what I would like you to do is pause the video and see, can you sketch what the function is based on the information that you're given in just the graph alone, and see what you can come up with. So pause the video now, sketch the function, and then when you're ready, hit play so you can kind of see how I'm going to do mine. All right, so ideally you've sketched your function and you have everything that you need. So what I'm going to be able to do is I'm going to look at this part here. Remember, this is the derivative. Here, the derivative is f prime of the function. This is greater than 0 here. Same thing here. So here, f prime of x is greater than 0. That means that the function needs to be increasing. So here, f, not the derivative, f of x must be increasing. Same thing here. F of x must be increasing. Now, here, on this part of the quadratic, we're showing you that the derivative, since it's less than 0, tells me that my function itself must be decreasing along that interval. The other thing that we identify here is that this point and this point, those are critical numbers. That are going to indicate where I have a maximum or a minimum value at. And the vertex of the parabola, that is going to represent the inflection point on the function. So let's see what we can sketch here. Let's pick a color that I haven't used yet. So I know I'm going to be so here I'm increasing. So I'm going to have a maximum here. I'm going to be decreasing here. So I'm going to have a minimum down here. So my function is going to kind of come up something like this. Maximum turn. And so now it's going decreasing along this interval. Where do I touch the x-axis? I don't know. I just know that somewhere here I'm going to have an inflection point about right there where it's going to change from decreasing to increasing and come down, come down, come down, and then turn and then go up like that. So I didn't get this point here, but this is my minimum. Here's my maximum and my inflection point, and that's essentially what the sketch of the function should look like. It may not be exact. If we knew values on the quadratic, we could probably pick some better points to sketch the given function. But again, we know it's a quadratic. So if the derivative is a quadratic, then the function that it came from had to have been a third-degree polynomial, and so that very much tells us a good idea what the shape of the function is going to look like. And it would be continuous, like so. I think that's about it. So that's what we're going to be looking at for curve sketching. I hope you all had got some good information from the video here, working through these examples. And if you guys have any questions, you know how to get in touch with me. And I look forward to seeing you in class soon. So thanks for watching, guys. Take care, be good, and stay safe.